years.
So,
Barry, you want to introduce Sarah?
Okay, so Sara is a PhD student here at UConn, and today is going to give a talk about provable security for PKI schemes, which is going to present at ACMCCS.
Questions, comments until after the presentation, please, because we're trying to get to right. So, so in the second talk, we get to say for so the discussion is very well done. The questions, comment, everything very important, but jump after the talk. Okay? And it will be very quick.
Hi, so I'm Sara, Wrotniak, and I'm going to be presenting provable security for PKI schemes. As my name said, I'm a graduate student here, and these are my collaborators, Hanbin, and Amir Harrisburg. So, so the focus of this talk is public key infrastructure, PKI, and it's really the foundation of applied cryptography. Because applied protocols, right, they assume they depend on authenticated keys for many of their properties, right? Like basic properties like confidentiality and authenticity. And to get authenticated keys, we use a PKI, right? So we will define what a PKI is in our work, but just intuitively, it's these mechanisms that allow a party to receive a public key and to authenticate it. Right? So this is usually done using certificates, which are signed by these special entities called certificate authorities. And so we need PKI, but we not only need PKI, we need it to be secure. So so what might be surprising is that many cryptographic schemes, right, have been well defined and have provably secure constructions for a long time. But for PKI schemes, this is not the case. And as engineers Goldreich said, it is not possible to build a cabin with no. It is possible to build a cabin with no foundations, but not a lasting building. So, this is something that's lacking, and so this is what we've done in our work, is to define security requirements for PKI and provide proofs of security for widely deployed PKIs. And I will mention which ones soon. So you might be wondering why the security of PKI schemes hasn't been defined previously. And some of the reasons might be historical, because originally PKIs were just applications of signatures, so their security might have seemed to just follow trivially from these signatures, the security of the signatures. Later PKI schemes became more complex with additional features like certificate chains, verification, extensions, time. In particular, properties for PKI schemes, they depend on time, like verification, transparency. And there's multiple parties and different requirements. So these might be why it took so long. And just before I go into more of the requirements that we define and what we've done, let me just remind you a bit about the background about PKI, although some of you might already know this. So as I said, PKI depends on these certificates, which are authenticated by using a PKI. So the main entities that are involved are the certificate authorities, or CAs, relying parties, which are like the browser and subject. So the subjects are like web servers, and the relying parties are the users of these websites and the certificates. So what happens is that the relying party, like a browser, will somehow it should know the public key of the certificate authority, like maybe hard coded into the browser, and then the certificate authority will issue a it's also called an issuer, will issue a certificate for the subject with the subject's public key. So it will sign that this key belongs to the subject, and then the subject can send this key to the relying party in the certificate. So the party can check, is this content coming from the subject, and validate it using the certificate authority's public key. So, and then there's also an expiration time in the certificate. So at some point it will expire. And multiple standards have been defined for PKIs and certificate frameworks. So the first one's these X509 standards. And then there's PKI-X, which kind of takes these X509 certificates and CRLs and profiles them for the internet. And then more recently, there's certificate transparency, which provides additional properties, in particular transparency. And also there's RPKI, which is for routing resource public key infrastructure. And the green ones this is what we analyze in our work. These are widely deployed PKIs used in today's infrastructure. So in our work, we analyze these systems, these existing deployed PKIs, and we kind of identified these 4 main properties, and then we defined the requirements for them. So these are for unforgeability, accountability, revocation, and transparency. But due to time constraints, we won't have time to go over all of them. So I will use revocation as the example here. And it should give you an idea of kind of our approach that we used in defining these requirements. So what is certificate revocation? We're going back to the previous figure, which gives you an idea of the typical situation, right? We have the CA, the subject, and the relying party, and now the relying party has the certificate from the subject. But what can happen, of course, is that the key of the subject might be compromised or exposed. And at this point now, the attacker can launch an attack on the subject because it knows of the secret key of the subject. Attack the relying party. And this whole time from the time of exposure until the expiration time is open for attacks, right? It's this whole window of exposure. But then the subject might detect this exposure. And so what it can do, what we'll want to try to do is limit this window by revoking the certificate. So it'll tell the CA, I want to revoke the certificate. And so ideally this window would now shrink, and everyone would find out that this certificate has been revoked and not trusted anymore. But in reality, it takes a bit of time. So there's an additional delay. And then finally, the browser will also know that the certificate has been revoked and will block the attack. So question is here, why there's this additional delay? So the reasons for this are, first of all, the certificate revocation information is actually not sent by telling the airline party that this certificate has been revoked. Rather, it's done periodically, basically informing the airline party that a certificate hasn't been revoked if it receives this periodical information. And there are different mechanisms, but the simplest one is the CRLs. So it's a list of the revoked certificates. And so since is done periodically, there is some delay until the relying party will find out. In addition, there's also network delays and clock turns. So we arrive at this kind of informal definition of our guaranteed delta revocation requirement, as we call it. So basically, if a benign CA revokes the certificate at some time, then from time t plus delta onwards, the relying parties should consider the certificate invalid. So they should no longer trust the certificate. But is this achieved in currently deployed PKIs? And the answer is no. It's actually not, and this can be surprising because we would expect that this seems like what we would expect from revocation, right? But it's actually not achieved by X509 v3 and PKIX. And we found this discovered this simple attack. It's not complex, but it wasn't clear to us until we formally defined the property and analyzed the PKI. So just to give you an idea, and this is even a simplification of the actual attack, but the issue is that in the normal case, CA will send a certificate to the subject, and the subject will ask to revoke it, and then the CA will issue this CRL, which includes this certificate saying that now it's been revoked. But if the CA is not benign, if it's and then the relying party will no longer trust the certificate. But if the CA is not benign, right? If it's a bad CA, it can just issue another CRL because it knows its own key, and then not include the certificate. So now, if the adversary sends this to the relying party will think this certificate still hasn't been revoked, so I can continue to use it. And we'll accept it. So note that although this isn't achieved by PKIX X793, it's not impossible to achieve it. Actually could have been done by just modifying PKIX to use to simply require, for example, one way to do it is to require that the CRLs are signed using the same public key that is used to validate the certificate itself. But even though this is an achievable property, we, based on our analysis, we defined this weaker requirement as well, accountable delta revocation. And the idea here is if revocation fails, then at least we should be able to find an accountable bad CA that's responsible for this. And this is actually achieved by PKIX, and we show this. And we have similar observations regarding transparency in the paper. So now this was all kind of informal. Of course, our focus is to have formal definitions. So how do we actually define it formally? We do it using this framework called MOS, which because it's a bit more complex than defining properties like for classical cryptographic schemes like signature schemes or encryption schemes because of the involvement of time. So we use this framework, MOS, and in MOS we define requirements and separately define models. So specifically what we assume when we analyze these PKIs. So this is how we define the guaranteed and accountable delta revocation predicates, and we won't have time to go over them here, but they are defined as precise functions. And using this function here, but it looks like I won't have time to really go over it, but it's in the paper. And the models, as I mentioned, in MOS we separately defined models, including correct initialization, corruption, and bounded clock drift, and they are also precisely defined like this. So our theorem about accountable delta revocation is that PKIX satisfies accountable delta revocation under this model, which is what I just described, and with respect to this delta. And in the paper, in the full version, actually, in ePrint, we have a formal proof by reduction based on this model and the deltas. So in conclusion, we we have made these contributions. So we analyzed the widely deployed PKIs, like 509v3 and PKIX with CRLs, as well as CT. And based on our analysis, we defined security requirements for PKI schemes. And we created proofs of security for these widely deployed PKIs. And the paper and the conference and the full version contain the definitions and proofs. And there remains more work to be done in terms of defining other properties and analyzing other PKIs. So yeah, we'll be happy to answer any questions.
So I'll go ahead and start. So in slide 10. Nine, sorry. So, sorry, why should I? No, the one you just got up, it's the Sara one. Hey, I was right, it is 10. Why should I expect any security when the CA is bad?
So the way we define this revocation requirement is that it should work if the CA is benign. So this figure is a slight simplification because really there's a certificate chain, right? So it might not be the immediate
Since figure is missplit, we should really fix this figure.
there's yeah, the figure is a bit simplified. So right where you see the bad CA, right, that could be a benign CA, and then up the chain further there could be a rogue CA, and this is really part of the main issue.
You should think about it this way, right? And really should be this, so if fix it to be like that. So you should have like here or on the side the same good CAs before, right? Yeah. Probably actually here we, it would be best to keep it as before in the same place. And maybe here on the side we'll put the bad CA. The bad CA is issuing a certificate to a fake copy of the good CA, right? So it should be the same name of the CA, maybe we add the name or whatever, so it's more clear. But it will be, of course, a fake one, so I don't know that or whatever. So it's not a real CA, right? It's just issuing a certificate for this other one, and that other one is issuing the CRL.
Okay, so just to restate my, so basically, current schemes, I don't get delta revocation if there's some adversarial CA somewhere on the path to root.
Okay. Some say who would issue a certificate.
Right. And so my hope, what is the achievable property? The achievable property is revocation as long as not all CAs on the path are bad.
No, actually, the achievable one is that we say if this is the case that there's maybe there was a rogue CA on the path, and so revocation didn't work, then we should be able to identify the CA.
Okay, so I think presentation wise, like, I guess I'm probably roughly your intended audience. Like, my immediate thought when you went through this is, I can't expect anything if my CA is bad. Like, why should I hope revocation to work if my CA is not going to revoke anything? So, like, any ideal functionality I can imagine, or right, like, the CA is not going to listen to any instructions, so there's no point of having a CRL. So, like, I think you do need to make this more complicated to show, like, there's some party acting honestly, there's some party who's, like, sending the CRL first, and, like, there's two versions, and, right, which is the zombie part, right? There's two versions of the CRL, the real one, or one, I guess, doesn't even get generated.
Maybe we even add the good CA. Let's see, we put the bad party somewhere, right? The attacker. And we show the attacker using the certificate because they got the private key, right? And then we have a vocation, right? And then we have the CRL, and the lying party stops accepting the certificate. And then we add the bad CA, which is issuing next year end for the certificate. Also, but also we emphasize this, the bad part of it.
So the other thing I wanted to say is mostly a comment, which is slides 11 through 16 are way too fast. And I know you have to be fast, but you cannot present. You cannot present both what MOPS is and what these deltas are and the model, and like you just don't have time to do it. So like my thought as I was going through this is you have a like rough, hey, here's an example. So you talked about 4 requirements, 3 PKI schemes that you analyzed. You show an example where these PKI schemes don't meet the requirements as you would expect it. It would be good to fill out that matrix for people. I think that's what I would try and do. And it, by the way, is that matrix like none of them satisfy it? Like transparency, accountability, right?
No, some of the properties are satisfied, or the weaker versions are. We actually have like some sort of a table like that in the paper, so we could probably include it here.
I cannot include the paper it's simplified.
Maybe simplify it.
Right, but I think if you said, hey, roughly revocation is captured by this scheme and not this. Transparency is captured by all 3. Like for people who don't understand your formal analysis, that's still a take home, right? Because you've done it with revocation, but I think saying, hey, we use MOS and this is like formally defined and proved, like that's a good idea, but you don't have time to do any of the, here's an actual theory statement. I'll be quiet.
So my problem could be really stupid, but the thing is like, you were mentioning, so, actually the or a security requirement actually come from the signature, right? So may I know what's the, current, challenge or disadvantage that the requirements come from signature? So, I mean, the overall, for me, it's not clear what's the motivation of this, work, like what kind of problem you just addressed.
So I think maybe what you're asking is like, what's the difference between just signatures and a PKI? Right, so a PKI, it allows us to have these CAs like in this figure. This whole, it's kind of like, this is a figure of this whole infrastructure. This is more than signatures because we have the certificate authority, which is special like entities that we trust. Like they can sign these certificates can get revoked, and there can be like chains of them, right? So this is all like, and not just a signature, right? So like more mechanisms to analyze, and as I mentioned, there's like the issue of time. So a definition of just a secure signature scheme, it doesn't really involve time, for example.
So can you go back to the last slide?
This one.
Yes, this. I think what would help here is, hey, later PKI schemes are more complex to define, blah, 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 blah. Here are attacks that go from all these complexities.
I think we should clarify, it's not the more complex defined, there are more complex, the more complex design, more additional, more complex properties, and therefore they require analysis because and we actually show that we found that if they could have flows people don't expect.
Right, but I think for a CCS audience in particular, saying this complexity has led to attacks. Like past just nobody's saying I can forge a signature, or I guess there have been a few of those, but like there's protocol downgrade, like there's tons of attacks here. And if you say this complexity has led to attacks, it's worth formalizing the actual goal. Like that's your argument of why this is something we're doing.
everybody in CCS knows that many times the weakness is in the system, not in the handle. It's a case that's right. That's what Ben is basically saying. So we can actually just say this here, that PKIs became complex systems, right? So there are system vulnerabilities which
Right,
do
like,
not involve a failure of the signal.
right, like we know NTP is a super complex system that is very easy to get wrong. And so you mess with NTP, everything with PKI falls down, right? Like all of these things are complex systems and they can all be attacked and have been attacked. Sorry, not can be, they all have. So maybe mostly for people who aren't like directly in this area, how much of this made sense? When did you get lost?
Yes.
Okay, let me rephrase. For people who have had a crypto class and maybe like, but no more, you don't do research in crypto. Were you lost like on slide 2? Were you lost on slide like 8 or 10 or the very end? Hey, you're probably like exactly the target audience. Wow. No, like how far did it make sense?
It made sense, most of it.
Right, when?
You know, I mean, there was not a point where I was like, I got lost. It made sense.
I've never done anything crypto. I think I could follow along with slide 9.
So 9 was the bad CA, or 10 is the attack, the zombie attack.
Justification.
So I mean, honestly, I think with 12 minutes, you're gonna have time to do this and present the attack, and then you're gonna.
You did run of saving like anyway.
Right, that's what I'm saying.
You did exceed like not by that much, but by several minutes. You did exceed.
Minutes is short.
It's very short.
Do what they do at crypto. A bunch of them would like go out of the time and they'd be like, yes, I'm about to finish in 2 minutes anyway. So the program chair would be like, okay, I'll let them speak.
Oh.
And then almost 2 minutes, and they're like, yeah, 1 minute.
No, CCF is too big. They boot you off the stage.
Okay, so any other questions or comments, or should we?
So just one question that I think you're likely to get is, okay, so you showed one particular attack. Is there any interest from the standards body in incorporating your results? Have you started that conversation?
Well, we know the answer is, we haven't like looked into, right? The standards bodies, doing anything about this attack, I guess, right?
I think that the point to access the standard bodies is only when we have a design which addresses these flows, right? Because that is not what we, at least for the occasion, we don't present that. We do say it's possible, but we don't actually present that as in this work, I mean, or in a good viable design that addresses these flows, we don't present in this work. It's something we have kind of in the pipe, but we don't yet present it. So we didn't even propose it because we don't have a solution. Just there's nothing in solicitation that they will do, but oh, we have this ability. Okay, what do you do?
You know, I don't have a solution for you here, but if I was, you know, Eric Briscorla or whoever, like the X509 V3 body, like, be like, why is this the first time I'm hearing this? Right, like, I would either be, this is an attack on my standard and I should have heard about it beforehand, or it's not an actual attack, like, which is it? So I think, right, you want to be a little careful with saying, no, this is not like a formally defined property in X509v3. How, like, this is our analysis of what delta replication should look like. And so like different people are free to disagree over whether this is an actual attack, because like, I don't know if there's an implicit assumption in X509v3 that the entire chain is benign or not. But I think you just have to be prepared for someone to say, like, have you done coordinate, whatever the current term for responsible disclosure is, coordinated vulnerability disclosure? No, that's not.
Disclosure.
I thought they changed the name. Anyways, no.
Yeah, like this attack, I think it wasn't really like the focus of our paper, right? And so, yeah, I mean, you should say, like, emphasize that this is what we think, what seems to us to be a good definition of, or like guaranteed delta replication. And this attack would, doesn't adhere to the definition. Okay.
Well, let's think. And before we complete.
Hello, can everybody hear me? Hello? Can everybody hear me? I don't have any feedbacks from the audience, so
I can hear you,
okay.
but I don't know if the audience can.
Okay, I'll go start the presentation. Hello everyone. Thank you so much for having me here today. I'm really excited to share our latest work on adversary black box attacks against machine learning models. So in this project, we introduce a normal black box attack strategy that can successfully break SOTA defenses with guaranteed attack success probability. So machine learning models have been incredibly successful in many areas. One of the simplest tasks.
Sorry, Hanbin, can you please wait? We haven't set up your presentation in the room yet.
Okay, yeah.
Sorry.
Okay, Hanbin, can you go to the beginning of your slides? Because we weren't seeing it here.
Okay.
And let's see. Is the sound coming from the room or is it from my laptop? Can you speak? Let's see if
Yes.
it's coming from my laptop. Okay. Okay, so Hanbin will be presenting his work, which will be presented in CCS in 2 weeks, I guess, on certifiable black box attacks with randomized adversarial examples, breaking defenses with provable confidence. Okay, so the floor is all yours.
Yes. Thank you so much to introduce me. I'm really excited to share our latest work on adversary black box attacks against machine learning models. In this project, we introduce a normal black box attack that can successfully break SOTA defenses with a guaranteed attack success probability. So machine learning models have been incredibly successful in many areas. One of the simplest tasks is classifying a picture of a dog into the correct category. But however, it's actually quite easy for attacker to create small changes or perturbations that can trigger the model. One common type of the attack is called black box attack. So in this scenario, the attacker can only has access to the input data and the query results, but not the model internal parameters. So using this limited information, the attacker can generate malicious perturbations based on the feedbacks from the model's hard label or prediction scores. In practice, black box attacks usually start by finding an initial perturbation that can fool the model, then refining it to make the perturbation as small as possible. While empirical black box attack can achieve high attack success rate, they are usually easy to detect or disrupt. This happens because during the crafting process, the attacker typically makes small updates to the perturbation in order to avoid unpredictable feedbacks. So detection methods like black light take advantage of this by identifying similar queries, which allows them to detect almost 100% of the existing black box attacks. Another way to defend against these attacks is by adding random noise to the inputs or the model parameters or the outputs. This makes the attacker's queries unstable and unpredictable. So many recent defenses methods, they have used this strategy to tackle with the black box attacks. So does this mean machine learning systems are now secure? Well, not exactly. If an attacker adds their own noise to the query, detection methods that rely on similarity checks may fail. However, while noise can disrupt the detection, it also impacts the attacker's ability to craft the malicious attacks. So the key to bypass strong detection and defense mechanisms is to use high randomness while still being able to accurately assess the situation to resist random disruption. So these two goals seems to conflict, making it difficult to create a method that can balance both. However, this change reminds us of a technique from certified defense, which is called randomized smoothing. So in randomized smoothing, model owner adds random noises to inputs, and there is a theoretical guarantee that a certain neighboring areas around the inputs will still remain in the original class. So this interesting idea leads us to ask an important question. Can attacker add noise to adversary examples and still guarantee that the noisy inputs stay in the adversary classes? To answer this, we developed a new black box attack called certifiable black box attack. First, we model adversary examples as random variables in the input space, following an adversary distribution. Second, we design a randomized parallel query process to query the target model with noise. Third, we build a theoretical framework to bound the success probability during the attack crafting. And finally, we create a normal frameworks with several techniques to craft and refine the adversary distribution. Compared to existing empirical attacks, the certifiable attack has several advantages. First, random noise helps it bypass the similarity detection, and it still maintains a high ASP. Even when model has a randomized defense mechanism. So this is because attack gathers statistic information from how both the model and the defense mechanism work together. And second, unlike empirical attacks, which targets a specific vulnerability in individual adversary examples, the certifiable attack explore an entire adversary space under an adversary distribution. And this allows the attacker to generate an infinite number of adversary examples due to the high dimensional continuous space, and all of them come with a guaranteed ASP. Third, empirical attacks typically keep querying the model until they find an adversary examples that works. So in a certifiable attack, it comes with a unique feature, like it guarantees that any sampled adversary example will have a provable minimum attack success probability without needing to verify it on the target model. In other words, the model has never seen these examples before, but they are still guaranteed to succeed with a certain probability. And in the next 3 slides, I will briefly walk you through the methodology. For more details, feel free to check out the paper. We define a certifiable attack in the context of classification. Given an input, a label, and a pre-configured attack success probability threshold P, the certifiable attack aims to find an adversary distribution phi with a mean x prime and a parameter kappa. So the data sample from phi should have at least p probability of being misclassified. To calculate this probability, we design a randomized parallel query process. In each batch of the query, the attacker sample noise from the distribution and add it to the inputs, and then query the target model in parallel. By using hypothesis testing, we can determine the lower bound of the ASP. With this technique, the goal of the certifiable attack is to find a distribution where the lower bound of the ASP is higher than the pre-configured threshold, while also minimize the size of the population. So now let's explore how we can find an adversary distribution and generate specific adversary examples. The first step is localization, which aims to find an initial adversary distribution that meets the required definition. We use deterministic algorithms to iteratively adjust the mean of the distribution until the randomized parallel query returns a probability higher than the threshold. At this point, we have an initial adversary distribution that gives us the desired ASP, but the population may be large. So the next step is refinement. Here we reshift the adversary distribution toward the clean inputs until it intersects with the decision boundary. During this process, we want to make sure that the ASP remains guaranteed. So to do this, we derive a theorem that gives us a bound for the shifting vector data. If the shifting vector follows this equation, the guarantee will stay intact. The challenge is figuring out the shifting vector while staying within this constraint. So once the refinement is done, we can start sampling adversary examples from the final adversary distribution. While this example already have a guaranteed ASP, the attacker can still query the target model with them to verify their success. In this work, we developed 2 localization algorithms and 1 refinement algorithm. The first, smooth self-supervised localization, use a surrogate model and a self-supervised probation to search for the adversary distribution. The second, a binary search method, starts by randomly selecting a distribution and then iteratively reduce the probation using a binary search. For the refinement step, we created an algorithm that determines the shifting direction by exploring the geometric relationship within the decision space. The shift is made according to a constraint from our derived theorem, which is similar to navigating within a certified radius. This ensures that the ASP is stay guaranteed. So in our experiments, we first weighted the theoretical lower bound of the attack success probability by comparing it with an actual ASP. So for this 4 example, we sampled 1,000 adversary examples and tested the empirical ASP. The results show that the empirical ASP always higher than the predefined threshold P. So this confirms the guarantee provided by our method. And next, we evaluate our attack against the SOTA defenses and compare it with SOTA empirical black box attacks. We select 4 representative defenses, including black light, random pre-processing, and post-processing defense, and trace adversary training. So our attacks was benchmarked against 16 SOTA black box attacks. After going through all the settings, we conducted hundreds of experiments to validate our claims. All of the settings and baseline methods can be found in our code, which is available in GitHub. So here we are presenting some partial results based on our experiments with ImageNet and RaceNet. After reviewing all the results in the paper, we have identified a few key findings. In all of the black light evaluation, our certifiable attack maintained a 0 detection rate, while the lowest detection rate for all the empirical attacks is 86.5%. And under pre-processing defense, the certifiable attack consistently achieved over 90% average ASR, both before or after the defense, while the ASR of the empirical attacks drops significantly. And in a post-processing defense scenario, the ASR of hard label empirical attacks dropped significantly, while the score-based empirical attacks has a slight reduction. And meanwhile, certifiable attacks maintain an ASR above 90%. So we also ran extensive experiments on adaptive defenses and conduct many ablation studies, and none of the evaluated defenses were able to significantly degrade the performance of our method. So for more detailed results, please check out our paper. And to wrap up, our work presents a first certifiable attack theory based on randomization in a black box setting, along with a normal attack framework featuring multiple localization and refinement method. and we conducted comprehensive evaluations. And looking ahead, our future work will focus on making localization and refinement more efficient and finding more optimal noise distributions and exploring its extensions to other domains. Thank you for your attention. So, any questions?
I'll start off with a couple. This is Ben again. So at a fundamental, so I understand the like drawing a ball in the adversarial class is different than what's been done before. But how is pulling your sample from the adversarial class to your starting image fundamentally different than pulling your starting image to the adversarial class? What's different about these two approaches?
If I understand correct, you are asking what is the difference between pulling the adversary, the examples in the adversary class and the benign class, right?
Right, like normal attacks pull the benign class to the adversarial class, and you're doing the opposite.
Actually, we are not doing the opposite. We are doing the opposite to the certified defense, which is in the defense side. And we just we use the similar techniques in defense, but now we are doing the attack.
Can you go forward one slide? So the smoothing makes total sense to me why you would do that. One more slide, sorry.
Like here?
No, other way. Forward like 3 slides. 1, 2, 3. One more. Keep going. One more. Sorry, I know this is annoying. The one where you show localization.
Localization.
Yes. Yeah. All right. Good.
Okay.
So, go one more click on this. So why do you refine by moving the adversarial example rather than trying to bring the target image to your distribution? Why refine the thing in the adversarial class instead of X in the original class?
Oh, because I'm asking why we find the distribution in the adversary class rather than in the original class, right?
No, I'm asking why you find delta in the adversarial class.
Yes. Delta. Yep. Why we find the data in the adversary class, right?
Instead of in the original class. Why shift B instead of shifting X?
Okay. Because with this delta is the shifting vector, and the goal of finding this data is to shift the adversary distribution close to the clean inputs, but we don't want to close the decision boundary because we want to maintain the adversary example like in the adversary class. If we go close, if we pass this boundary, then it's not an adversary attack.
Yeah, and second, I guess, somewhat related question. So building this distribution fee takes a bunch of measurements in the adversarial class. Yes?
Yes.
Okay, so is that detectable?
Oh, yeah. This is a good question. We actually we have we have done many experiments to detect the noise or detect the queries, but in as I showed before, in the results, the detection method based on the query history cannot detect our method because the noise is different each time.
Well, sorry, current techniques can't detect it. Could you
Yes.
build a detector?
So sorry, what is that?
So, right, it's different to say this attack is undetectable versus saying current detections techniques don't work.
Yeah, current techniques don't work.
Okay. Do you
Yeah.
think it's possible to build a detector? For the
Oh, are you asking about like taking a similarity metric between one query and the next? Those defenses already exist.
But they don't work for this because it's a different way of moving around the space. So I'm asking,
Yes.
can you build a detector?
They don't work because the significant difference is our attack includes some random noises. So some potential detection that we can imagine is like to detect the noise, but we have also tried that methods, and that doesn't work if the noise scale is too small.
So I would add this to your talk saying that you have tried specifically to detect this, not just using prior work. I think that's an important thing for you to say.
Okay.
And my only comment, and then I'll let other people go, that set of 4 tables, there's not a single number on it that's visible. Just get rid of that slide. The charts you do after are fine. Like literally not a single thing on that is visible. Just get rid of it. You
Okay.
don't need, what you have after is fine.
Okay, thank you.
At least for me, maybe I'm old, but I can't. Bandit. I read the word bandit. Other questions?
Yes, what's the strategy for so I feel like that part is actually, I mean, that part should be the contribution of your work, right? So I feel like that part is not. So the coverage.
Sorry, I can't hear. Like, is that Shuya is asking question?
Yeah, one.
So I feel like the delta, because you explained to me before, right? So the delta, how you refine the delta should be the contribution of your work, right? Of this work.
Yes.
So I guess people here, we don't really understand a lot what's the art of this delta, how you refine the delta. I guess this part you can make it more clear.
Okay.
Yeah.
Okay, that's a good suggestion. Yeah, maybe I could go so quick in this part. So are you suggesting me to do it like in the next talk, or are you asking questions?
I think we're doing both. We're asking questions.
Okay.
And giving you feedback for what you could do.
Okay. Actually, here in this part, I missed like some algorithms and the details of the methods. I just like want to go through the basic logic behind this. So let me clarify it more. Like the data is to the purpose of data is to reduce the perturbation, and how to design this data is actually it's complicated. First, we need to decide the data's direction, and second, we need to decide the data's distance or the scales. And for the direction, we use like a geometric relationship. We want to shift the distribution close to the decision boundary. And for the distance, we want to like maintain the guarantees of the distribution. So this theorem is for this purpose. If the data is moving within this condition, then it won't break the guarantee. So by solving these two equation, we can get the distance of the data. And yeah.
I guess you have the same normal problem here, which is that you can hit a local minimum for the distance. And you have to use, randomization to get out of that local minimum. Right? You move in a direction that's going to close the distance, but it's actually not like your global best direction to move.
That's true. That's true. We cannot like achieve the global minimum because that's pretty computational costly.
But
So
you can guarantee a attack success rate, just not like a particular noise perturbation level.
yeah. That's true. Like for a particular distribution, we can like find the local minimum and we can guarantee the attack success rate.
Actually, because of the defense that you suggested, that we might be able to denoise it and make a defense to combat this adversarial noise. I remember, because I read his paper before, he had the experiment on using diffusion models that maybe we can try to denoise it adversarial examples, and then he showed that it's not working. So I think like for the result part, I think this can help the potential question of maybe we can reverse the noise. So I think, yeah.
Yeah, that's a good suggestion. Actually, I make some backup slides for the diffusion defense.
So I don't think you need to present this. You just need to say, we've tried to detect our noise without much success using like adaptations of state-of-the-art methods. Yeah, because recently there are some work showing that we can always reverse the adversarial noise, so it can somehow shed light on this doubt. So yeah, that's
Okay. Okay, I will figure out how to add these like results or maybe just mention it. Yeah, as you suggested. Okay, thank you.
questions or comments from online people too? Or anybody else in the room?
I just wanted to clarify that when you're specifying something about the fence, you're not referring to adversarial training, right? You're referring to something that takes a similarity metric between, say, two separate queries, right? And or after, you query the model enough, it will just cut you off. Because it seems like in your results page, you're listing, you do list the number of queries that you have. So I'm just wondering if you're working under assumption that after, say, 1,000 queries, you'll be cut off?
What do you mean by cut off?
Like you're trying to attack a defense that will limit your query budget.
The quota budget, right? Yes, we for all the experiments we have a quarter budget or the malicious budgets.
Okay.
Yeah, it's around like 10,000 for in all the experiments. Like, yeah.
Okay.
And actually, the query number for our work, for our method, is no larger than the empirical attacks.
Right. And when you mention defense, are you also referring to your diffusion model that you showed us on the other slides? Because you don't have results for a model that was trained using adversarial examples.
Oh, yeah, we don't have that results because it's not what we want to highlight.
Right.
But we do have the results here, but just too many results. I don't know. I don't want to like go through everything.
So just the other thing I just wanted to clarify is, could you go to the result page where you have results for the diffusion model?
Diffusion model,
Yes.
yes.
Is that a diffusion defense that was trained to denoise, say, like white box generated adversarial examples? Or is that just some denoising autoencoder?
What do you mean? But like, can you restate your question?
Was this diffusion model trained on, say, white box adversarial examples?
Oh, no. The diffusion model is trained on the noise scaled, but with the benign images or the clean images, not on the adversary images.
Okay, so it's just you're taking some Gaussian noise and adding to it. Okay. All right.
Yes.
Thank you.
Yeah.
Okay. Are we all set? Any other questions? No. Okay, Hanbin, I guess we're done here. Thank you very much for your presentation. Let's thank the speaker again.